Welcome to Study Loop.
Hi everyone, thanks for joining me today. What we're looking at is a problem dealing with power, and what we're given to us is we have an elevator that has a weight of 6,600 pounds and it is connected to a motor shown here, and that motor is assisted with a counterweight shown here, and that counterweight has a weight of 2,200 pounds. What we're asked to solve for is the power supplied by the motor when the elevator is moving down at a velocity of 1 feet per second, and then at a velocity of up at 1 feet per second while decelerating at negative 0.18 feet per second squared. So what we're going to first do is just look at some lengths to relate some velocities and accelerations with each other. So what we see here is that this is going to be what we call LE. We'll call that here LE. And this is what we're going to call LW. Now this figure has been exaggerated just to show for illustrations, but you'll see that in the figure that's provided in the textbook that what we're going to do is going to make some algebraic sense. So what we're going to say is that LE plus LW is equal to C1, and what this basically means is that the length of that cable does not change. And what we're going to do is we're going to take the derivative of both sides and say that VE, which is the velocity of E, velocity of W is equal to 0. And then we're going to say, take the derivative again and say the acceleration of E plus the acceleration of W is equal to 0. And what this says is that AE is equal to negative AW. Now I'm going to draw a free body diagram of the elevator. And what we see is that there is a weight force, and that there are 3 tension forces, 2 tension forces which are the same, and we're going to call them T1. And then there's a middle tension force, which we're going to call T2. So if we draw this and write out Newton's second law, we see that 2T1 plus TW plus T2 minus weight is equal to MAE. Now I'm also going to draw a free body diagram for our counterweight. So we have the weight, and then we have that tension 2 force. So second law says that T2 minus WW equals MAW, and we can solve for T2 and say that T2 is equal to MAW plus the weight. And this is good because we can actually take this and plug that in for our T2 here in our elevator second law expression. So what that gives us is that 2T1 plus MAW plus the weight of the counterweight minus the weight of the elevator is equal to mass times acceleration of the elevator. Now, remember that for situation 1, the elevator is moving at a constant velocity of downward at 1 feet per second. So the acceleration of our elevator is going to be 0, as is the acceleration of our counterweight going to be 0. So these two terms conveniently are going to be 0 for us. So we can solve for tension, and what that gives us is 2 times tension 1 is equal to the weight of the elevator minus the weight of the counterweight. And we know these two quantities, so we solve that tension 1 is equal to 2,200 pounds. Now we know that the power that the elevator is experiencing is force times velocity, and that is simply tension 1 times velocity. We know that the velocity is 1 feet per second, so plugging that in, we get a power of 2,200 foot-pounds per second. Now if we want that in horsepower, that's going to be 1 horsepower over 550 foot-pounds per second. These cancel, and we see that the power experienced by the elevator is 4 horsepower. However, we know that the power required to give out by the motor is going to be 2 times the power experienced by the elevator, so that is going to be 8 horsepower. That is our final answer. Now we're going to move to the second part of the question, where we are now looking at a different scenario where the elevator is moving downward at 1 feet per second and decelerating at negative 0.18 feet per second squared. So again, our free body diagram is going to be the same, and our Newton laws expressions are going to be the same. So what we have for the elevator is 2T1 plus T2 minus WE is equal to MEAE. And for the counterweight, we're going to have something a little different. It's going to be T2 minus WW is equal to negative MWAW. So similarly, we're going to solve for T2, and we see that T2 is equal to WW minus the mass of the counterweight times acceleration of the counterweight. Now, similar to before, we're just going to take this T2 and plug it in right there. And what we end up with is 2T1 plus the weight of the counterweight minus the net force on the counterweight is equal to the net force on the elevator plus the weight of the elevator. Now again, we're going to solve for T1, and we're going to bring everything over to the other side. So we're left with T1 is equal, 2T1 is going to be equal to the weight of the counterweight minus the weight of the the weight of the elevator minus the weight of the counterweight plus the net force on the elevator plus the net force on the counterweight. Now plugging in for the variables that we know, we know all of these quantities because they're all given to us. We can solve for T1 to be equal to 2187.7 foot-pounds. Now similar to before, the power experienced by the elevator is going to be F times velocity, and for us that's T1 times velocity. And remember, our velocity is 1 feet per second, so our power is 2,187.7 foot-pounds per second. Now, as is before, the power that is required to be distributed by the motor is going to be 2 times the power experienced by the elevator, and that's going to be our PC, which is going to be 2 times 2187.7, which gives us 4375.4 foot-pounds per second. Now again, converting this into horsepower requires that we just divide this by 550 foot-pounds per second per horsepower. And this gives us a final power required of 7.96 horsepower. That is our final answer.